started doing it. I didn't realize it at first, but at the end of the day, that's what I was doing. And so if I'm doing it, it means that it can be done. Do I now think that everything can fit in nice and precise definition? No, physics is too complicated for that. The key is really finding which part can be put in the formal system and which part is better to leave outside of the formal system. It's really finding the line between physics and math. And this is what this video is about. I'm going to tell you what I learned and what I wish somebody told me 10 years ago. And maybe you'll find this interesting. Maybe you're gonna want to help me with your research. Maybe it's gonna be useful for your own research. But these are sort of the things that you have to keep in mind. But these are sort of the things.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2. Oops. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, sounds good. All right. Okay, I ate something. Now I'm okay. I ate and now I'm okay. Let me just check the audio on the Discord. No, the output should be the headset. Input is USB. What is the output? Can this be moved? Okay. So what is the output? Am I getting the right output? Audio, headphones. Yeah, it looks good. Looks good. Tastes good. Everything is fine. Okay.
When you are going to create a formal system for physics. So first, we should have at least a vague idea of what a formal system is. And a formal system, you can think it in terms of three main pieces. The first piece is the set of primitive notions that are in the formal system. These are the basic objects that are taken as is
Okay.
without any definition.
All right. Let me talk about. Let's talk about.
Welcome back.
Let's talk about what we want to talk about. Let's talk about what we want to talk about. So I want to talk about first. Let's get what were those videos names? Research this one, fiber optic. This one. This is what I want to talk about. Okay, copy and modify the current video's name to that. So fiber optics based interferometer to successfully non-null reproduce Michelson-Morely experiment. All right, so what do we got? All right, so we don't need that. We don't need to talk about anything. I just want to show you a few new designs. The question is, should I keep using the paintbrush, the whiteboard app, or it's not such a good app. It's designed for multiple people drawing together. I don't need that. What I need is just to draw. The question is, can I share a window? I'm just terrified of sharing windows. Where's the paint app? There it is. Okay, that's paint. I do Control O. Interesting. Okay, we're good. All right, let me just magnify the size of this canvas. But it's still, the problem is it's still going to be a canvas. So what's the advantage? I don't see the advantage. I might as well, it's too dangerous. I might as well keep using the Discord. It's much easier to use Discord. So let's use the whiteboard. I'll tell you about the new design. I guess we can close. We don't need this, so we can get a little bit more real estate. Let me create, fiber optics. That's the one, yeah. So we were discussing this previously. Previously, we were discussing this. So I'm thinking. Okay, this is the original interferometer. It's about 1 meter arm over a 90-degree rotation. Let's say we're expecting to get 1 wavelength worth of interference between these two signals. Now, assuming that the ether is flowing, this is from the east to the west. That's the assumption. We're in the north hemisphere. So that's our assumption. Wait, south hemisphere would be the same, I guess. I would think so. Yeah, I think in the south, right? It doesn't matter if you're at the north or at the south. The Earth is rotating the same direction, so the ether should be flowing in the same direction from the east to the west. So this is from the east to the west. This is the ether wind, so-called, the relative velocity of the ether. All right, so the ether is basically rain coming down. Since the Earth is rotating in Ohio, let's say, at 500 meters per second to the east, therefore, the effective velocity of the ether should be to the west. Oops. This is the ether wind, the effective ether wind. The relative velocity, right? The rain is coming down, but you're moving to the right 500 meters per second. So you should feel incoming ether at 500 meters per second. Okay. This is the Earth rotation from the west towards the east. This is the north. The Earth obeys the right-hand rule, so it rotates towards the north. And the sun rises, that's why the sun rises in the east. And that's why the ether flows from the east. The effective flows from the east. Okay. But the problem is you can never get, with these numbers, you do the calculation, you can never get not a single wave. You're probably not going to see anything. It's going to be very difficult. Maybe with very fine instrumentation, you should be able to see something. By the way, I think they were using 4 ways, so they were using 4 meters. It doesn't matter. It's still, I don't know. I mean, I don't know. They didn't have a theory of which way the ether should be flowing. They were thinking that the Earth is moving through the solar system, and that's why you should feel the ether. There is a secondary effect. And they were thinking about night and day. They were thinking that the ether is this solar, basically a solar wind. That's how they were. That was their theory. It's really not logical. So my theory is that gravity is the ether. This rain that comes down, it goes through things, goes through us, and that's why we feel compelled. We feel like there is like a sucking force pulling us towards the Earth. That force is gravity, and it's caused by the flow of the ether towards massive objects. Okay. Einstein said this pretty much. He didn't say it flows. He said the ether is gravity. So I don't know what he had in mind. He didn't think it through, I guess, but he had. It's not like I'm saying the ether is gravity and I'm contradicting everyone. So if you're worried about it, Einstein agreed with me in 1920 in Leiden when he spoke at Lorenz's University. All right. So anywho, wait, let me give you a link. If somebody wants to join us, you're welcome to join us. It's an open forum. It's an open forum. It's a public forum. Okay, so I don't know. I don't have access to Michelson's data or anyone else's data. I looked up at some researchers. I don't know what they did. Maybe they saw something. I don't know. So the least we should do is rerun this experiment, knowing this theory, and see if you're able to get a signal. That's nice. We're done. If not, so you want to build a bigger device. So there's many ways I've offered to build a bigger device effectively. So one way is to have many more mirrors. So you can even have 1,000 mirrors over 1 meter. So that's basically 1 kilometer. That should give you at least a wavelength per 90 degrees. But that's a big rig that you'd have to build. So today I came up with a new concept. Of course, you can use X-rays and gamma rays, but then these are not visible, so you'd have to have special detectors, and these are dangerous waves, so it's going to be difficult to conduct this experiment. So today I came up with a relatively inexpensive. So we watched a video about Professor Howe, that she's able to slow down light, but I don't know the budget that we would need. We would need to create a pool. Let's use the green, the purple, like a pool of frozen atoms, really frozen atoms here and here. And light would slow down significantly in this region. And when light slows down, the ether has more of an impact. The ether has more of a chance to impact, I'm assuming. Because, right, it slows down because of inner interactions, but during this time, ether is flowing through, right? Ultimately, light is moving based on the ether. There is a chain reaction, an interaction between the original light wave and the inner molecules, the frozen atoms and the frozen electrons. There is an interaction, but that just delays the original light wave, and the original light wave is based on the ether. It propagates through the ether. Now we cannot slow down the ether. The ether, everything we know are just waves in the ether. So every proton, every quark is a wave in the ether. So the ether doesn't have a temperature, obviously. So we cannot freeze the ether. So it's like there's nothing we can do to the ether. I cannot imagine anything we can do to the ether. The only thing we can do to the ether is drag it through gravity. Ether responds very well to gravity. It is the Higgs mechanism. So anyway, so it should be possible to put these puddles of frozen atoms and have these light beams go through them, but that could be an even more complicated apparatus than using gamma or X-rays or 1,000 mirrors or a space-based 1 kilometer, 10 kilometer, whatever. So today I came up with the fiber optics based solution. So according to the fiber optics based solutions, let me undo this. Anyway, so the fiber optics, all we're saying is basically that, let me think. So this red part, all we need, right? If we could have more mirrors over here, the more mirrors we have here, the more we are interacting with the ether, and the more we are, well, in this case, we're not slowing down as much because we're perpendicular. Our motion is perpendicular, so we're significantly less influenced by the ether. But this guy is more influenced. This guy supposedly is much more slowed down by the ether flow, right? This is the ether flow. So this guy, the yellow guy, is really slowed down compared to the red guy. Okay, so but not enough. Over 1 meter arms is not enough. So Michelson-Morely, I saw they put a bunch of mirrors, 4 mirrors, I think. But even that was apparently not enough. They didn't get a signal. All right. So the next step is the fiber optics solution. Fiber optics, all I'm going to say is, all it says is that this chunk, we can extend it. If we, instead of using a mirror here, let's forget it, let's drop this mirror. Let's just have a thread of fiber optics going back and forth. A spool will spool it back and forth, instead of a mirror. And imagine we'll have 2 mirrors. We're going to bounce this back and forth. And then we're going to let the signal, we're going to release the signal and let it go and complete the trip over here. And we're going to do the same thing over here. We're going to put a spool back and forth. So imagine we could just replace this part with a spool, because we could leave the mirrors. The mirrors don't bother me so much. Or you can remove the mirror and have a spool going back and forth. You don't need the mirror back and forth many times, and then let it go. It's going to hit the mirror and end up over here. So it doesn't really matter how many spools. It's good that you'd have the same number, because you want these 2 signals to arrive basically at the same time. But it doesn't really matter. You want to delay this by as much as possible and delay this by as much as possible. But we don't care not even about the relative delay between these. We care about when we rotate this thing slowly, we want to see the change in the interference. And this change will come about, I guess, even if we just delay one of them. We don't need to delay the other one. The problem is, as you rotate and this guy becomes the top guy and this guy is going to be over here, then you're going to lose the effects. Or maybe you're not, I don't know. So maybe first try spooling only this guy. So what I would do is, this is 1 meter. You could take a 1 kilometer fiber optic cable. Not a cable, just a single. All you need is a single thread, and just spool it over back and forth. Let's say 1,000 times, so it's 1,000 meters. That's one option. Another option might be that it's a cable. It's a cable that contains thousands of fibers. Maybe it's possible. Maybe it has a. I don't know. I mean, I don't know what kind of hardware is supported by these cables, but maybe it's possible to get a mirror, place a mirror on the cable and a mirror on this cable, so that a path is created. So you don't have to spool it back and forth, but just have a mirror in the cable and a mirror in the cable. I don't know. I don't know what's available. But if it's possible, maybe someone can produce such an item and sell it to labs, because this experiment would be used by, can be reproduced in high schools if they want. So you can reproduce it, and maybe somebody wants to sell this apparatus, because this is going to be extremely revolutionary if it comes out being true, which I suspect very much it will be true. This will be extremely revolutionary. This will be the beginning of a unified field theory. Because if I'm correct, then gravity is the ether, but then special relativity becomes just wave mechanics relativity. It stops being magical. But then also, I think this will influence quantum theory, quantum wave theory, the quantum field theory. It will, I think, it will influence it, because they'll stop thinking that the quantum field is imaginary. They'll start believing that it's a real thing, that the ether is real. It is the quantum field. So if I'm correct, this will change their perspective, and maybe they'll stop being so unmechanical in their explanations and so ethereal. Sorry for the double speak or double entendre. Anywho, let's check the audio. I think the audio is okay. Let's go. So yeah. So I think fiber optics are cheap, and it's not a lot of work. I mean, worst case scenario, you take some fiber optic cable and you just lay it back and forth 1 meter, just lay a 1 kilometer cable back and forth 1,000 times. It shouldn't be a lot of work. And then let it, and you can end it here, aim it properly so it hits the detector. It just needs to hit the same spot that the other one hits, so that you see the two circles. You should be able to see two circles. You can there's videos that show how to align an interferometer, and then you would do the same over here with this guy. Just spool it back and forth, 1,000 times. And 1,000 times should be enough for my calculations to get at least one wavelength. So this should not be expensive. Fiber optic cable, you don't need a cable, you just need a single fiber. You should be able to get your hands in one of those for very cheap. Let's see cost. La 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 la. All right, so what is the cost of a fiber optic, of an optic fiber? Based on the provided search results, here is a summary of the costs associated with fiber optic cables and installations per foot cost. The cost of fiber optic cable varies depending on the type, multi-mode. So it's $1 to $4 per foot, indoor or outdoor use. Single mode cable, not specified in the search result, but typically more expensive than multi-mode. I think you should be able to get, even at $1 per foot, it's basically, let's say, $10 per meter. So it's $10,000, but I think you should be able to reduce the cost. It shouldn't cost you that much. That's installation. Oh, that's how much it costs to install. Fiber optic. I don't want to install. I just want to purchase it. Federal law. According to one search result under federal law and an act of Congress, the cost of getting fiber optic internet. What's internet? Key driver fiber construction cost variances include labor, population density. No. I just want to purchase I don't want installation. I just want to purchase. So la 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 la. I want to purchase. Optic fiber. Optic fiber. I just want to purchase it. Shopping. Based on the provided search results, Diamond SA via where's the price? Single mode. Where can I just buy it? Just sell it to me. What do I need to install? No, I just want to buy. Where to buy? Where can I sell? All right. Who's buying? Who's selling? Fiber optic cable. I don't want the cable. I want the fiber. What you need to know. Ordering custom fiber optic cable. Fiber optic. Maybe we can go just to Amazon. There it is. There's a picture. Install. I don't want to install. Optical fiber. I just want to buy optical fiber. So they call it optical fiber. Optical fiber. No, I don't want to install beginner's guide. Optics. What is this? Google Glasses. Where can I buy? Where can I purchase an optical fiber? Based on your life, based on your previous life. Additionally, you can also find online retailers, Amazon and Best Buy. So let's go, I guess let's go to Amazon. Here's Amazon. Let's go. One second. Na 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 na. Na 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 na. Na 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 na. Na na. Na 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 na. All right, let's try this. Hello, sign in. Wow, she's hot. Jesus. Oh, that's Kim Kardashian. So what do we want? Oh, fiber optic cables. Oh my God, why is it so white? $8 for what length? Audio cable, optical audio, 6 feet. Amazon Basics, Toslink, digital optical audio. That looks like it. Optic internet cable. Oh, look at this. This is $300. This looks good. So this is 300 meters, LC to LC. I don't know what is LC. Armored outdoor fiber optic cable, single mode duplex fiber, patch cable, 125. Micrometers, LC fiber jumper, OS1, OS2 compatible, low friction. And this is $300. So it's about $1 a meter. So you buy So you can start with 300 meters. That's a good start. I would start with one of these. Now I was thinking you might be able to run the test directly on this. So you might not even have to spool it out. You could just put this, because you just need to have two opposing directions. So you can buy two of these, so it's going to be $600. And then I'll show you what to do with them. La 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 la. So what you could do theoretically, it wouldn't make any sense to put them, right? If you put one here and one here, that wouldn't make any sense. Like to have the light going in here and coming out here, light going in here and coming out here. That doesn't make any sense because there's no difference. You're trying to get a different effect. So you can't do that. That doesn't make any sense. So instead, what I would suggest is you place the roll like this, with the fibers going round and round this way. Here you would put it like this, with the cables going this way. So right there, in the roll, like don't even unroll it. Use the roll as is. And this will be the input, and this is the output, where in the middle, it's going to go round and round and round and round. It's going to go in, do all these rounds, and come out. But what it's actually doing is it's moving to the right and to the left. It's moving to the right and to the left. It's also moving a little bit up and down. It's probably moving a little bit up and down. So I don't know. This might not work. I don't know. You have to do the calculations. You actually have to maybe run a computer simulation or do an actual calculation if this will work, because these two might cancel each other out depending maybe on the radius, on the width, on I don't know. I don't know. I didn't go through the actual calculations. So this would be the input, and this is the output. 1 second, I messed up the output. This would be the output. So this might work. So you don't even have to unroll the fiber. So I'm saving you a lot of work. So you just have to invest $600 in this experiment. It's a next day. It's a next day experiment in the US. So next day, tomorrow you can run this experiment. You don't even need mirrors. You don't even need this half mirror, because you can just have, you need to split the beam. You do need to split the beam. So I guess you need either a half mirror or some beam splitter. Maybe there's a fiber optics splitter. Is there a fiber optic splitter? It could be enough. La 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 la. La 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 la. Let's duplicate this. Duplicate. La la la. I want a fiber optics. What do you call it? It's not a repeat. It's a T. It's a T. It's a T. A T. Okay, maybe there's no T. Maybe this is a T? The fiber optic fast, it's a connector. No, what we need is a splitter. Oh, there is a splitter, there is. So this is a splitter. So the input's 1 and there's probably, I don't know how it splits it. Blue, rigor, digital, optical. It's digital. I don't like that it's digital. It might be good enough. Audio splitter. It's optical audio splitter for home theater. It might do the job for $20. This would be a splitter. Otherwise, you have to use a mirror. I'm just trying to get away from anything that is out in the open, so we can have everything would be closed and ready to go. Digital optical splitter 1 and 2 out two slink. I don't know what it's two slink. Optical splitter 1 to 2 in 2 out. 1 in 2 out. Digital optical audio. Why are they all audio? Dolby JTech. Audio splitter cable. Okay. Anyway, this seems to be the price: $13, $14, $12. Optical cable. I'm assuming this is an optical signal. That this is optical input and output, whatever. I hope. If not, you're gonna use the beam splitter, but you might be able to use this for the apparatus. If yes, then you just have an input, some laser beam or a light source. You probably don't even need a laser beam, but hello, Amnesiac, how are you? Oh, I wasn't sharing this. Can you talk? Your mic is muted. Amnesiac, what do you want to do? You gonna talk? I'm not gonna talk. Okay, no talking. Anyway, so yeah, back to this guy. Yeah. Okay, Amnesiac. Oh my god. Oh, Amnesiac, no, stop. I don't want to have to remove you. No, stop. Okay. Yeah. All right, it's okay. Just don't destroy the actual science, please. Anyway, so we take the light source, we connect the T splitter to the light source, and this is the splitter. We're going to put the splitter here, so it's 1 in, and then it's going to be 1 out to here, and the second out to here, and that's it. And then the 2 signals will be displayed here on the same spot, and you'll see the signal. So this could be really good. This might work. If it doesn't work, then you have to spool it out, and actually it's some work. It's 300 meters. You have 300 meters, so 300 times here and 300 times here. 300 meters, I don't remember if it gives you a full wavelength, if it's a laser red light. Blue light might be better because it's a shorter wavelength, a little bit shorter, so you might see the effect better. The idea here with the roll is it's going this way. It's basically it's going round and round, but it's mostly, I would say, going this way, whereas this guy is going this way. So in this case, actually, if the ether is blowing this way, this guy will slow down more than this guy. And then when you rotate them, this guy is at the top, so it's going to be slowed down more. So basically 45 degrees, you should not expect think after 45 degrees, the direction is reversed. So in the first 45 degrees, right, right now, this guy, let's assume this is the ether wind, so this guy is slower. But at 45 degrees, they're identical. And then this guy becomes faster. And this one gets slower. So this one right now is faster. It's going to get slower and slower and slower and slower and slower. But at 45 degrees, they're the same. They're the same. So it's always, this one is always becoming slower and slower and slower and slower and slower and slower and slower. And this one is becoming faster and faster. Yeah, so over 90 degrees, you should get a progressive effect in the same direction, I think. Anyway, so it should be fairly interesting one way or the other. This should be able to do this in a high school setting or even in a middle school or preschool. This is really, or somebody at home should invest the money and run this experiment and give us feedback. It's really straightforward. So it's, I would say, under $1,000. This is a most of the cost here is the two fiber optic rolls. What do you call these things? Rolls? La 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 la. Share this tab. What do you call this thing? LC to LC armored outdoor. Or you can even conduct this experiment outdoor. Fiber optic cable, single mode duplex fiber patch cable. It does. I don't know what this thing is called. It's a roll. Anyway, let's see if anybody else. What about this guy? Oh, look, for $200. Well, it's half. It's half the size. 150 meters. So that's useless. 75 meters. So that's even worse. And 150 meters for 150. That's no good. Okay, that's basically the price. Really interesting stuff. This might not work because it's just not long enough. Maybe you need more rolls because only a little bit of the effect. I would say half of the effect is left and right, and half of the effect is up and down. Right? We're looking at a top view of the roll. Let me see if I have a picture of what we're looking at. La la la. Are there any other pictures? I want to see a top view. Is there a top view? Low tension, whatever. Oh, they're testing it for tension, I guess. Tension. Oh, tension testing. Zzz, that's good. Okay, it's tested for tension. Is this the same video? Testing machine. Okay, torsion. Oh, whatever that means. Oh, there's more videos for this product. Fiber patch. Whatever. It doesn't matter. It really doesn't matter. It's not critical. But this should be a really, either one way or the other, this would really drop the cost significantly. Amnesiac, just don't draw over here. I'm teaching this right now, so just don't ruin the drawing, please. Anyway, so oh my God, what are you doing? No, okay, you're banned. Goodbye. Server deafen, disconnect, block. Well, first I'm going to server mute you, server deafen, ban. Suspicious, compromised, breaking server rules, ban. Alright. Wonderful. That's it. That's what people want to do with their time. Like, what is wrong with people? I don't understand. Oh my God, Jesus. What is wrong with people? Okay. Alright, anyway. Let's get some water. Okay. So what I'm saying is that you're not getting the 300 meters back and forth. You're only getting, I would say, half a meter, half of the length is back and forth and half of it is up and down. Oh, but wait, up and down, yeah, up and down is not the full effect of the ether. Up and down is very similar to this. So this is going, everything this is doing is perpendicular to the ether direction, except for the fact that meanwhile it's also internally doing this. The way they spool it is it goes all the way here, then all the way there. So it is doing this action as well, but hopefully there's a difference. If you do the calculations, maybe there is a difference. It might be too small over a 300 meter spool. It might be too small and you might not get an effect. It might not be worth 300 meters, but much, much less. 150 or 75 or 30 meters, it could be really bad. So if you're not getting an effect, if you're not seeing anything noticeable, then you have to undo the fiber and just lay it out back and forth over here and back and forth over here. You can still use the splitter for $20 like we saw. So it should still come out under $1,000. Should be about, let's say, $700. You should be able to finish this experiment within $700, and that would be amazing. That would be awesome. If you have any questions how to conduct the experiment, you should be able to do this at home because there's nothing special. You might be able to feed it a normal light source. If not, it's a $1 laser pointer. A $1 laser pointer, you should be able to point it here and see that you're getting output from here and output from here. And then you can bring the fiber all the way to here and bring that's the red one. And bring this, you wouldn't be able to see. So let's say, yeah, let's make it this color. And bring this guy all the way to here and have them point basically at the same spot. Tape them down over here and have them point at the very same spot, and you'll be able to see these circles then rotate this entire apparatus. If it's horizontal, you can rotate, but also if it's vertical, if you're building it so it's vertical, or if you're building it so that you can change the angle of the apparatus, so you can run it both vertically and horizontally, then you get a bonus. Vertically, you can also measure. You can measure the very speed of the ether, the 11,000 meters per second. You should be able to measure that. I mean, that would be extremely significant. That would be very nice. So if you can build it, that's going to make it more expensive for you to be able to build it vertically. This is already a big jig, a big rig that you should be able to hold vertically and rotate, slowly rotate it and see the signal coming through. What you might also want to do is put a camera. You might want to put a camera because as it rotates, you want to be able to look at it or maybe display it on. Right? You can just put an iPhone here or something. A camera looking at the spot. So this entire rig. So now you have this entire rig mounted on something. So now you have a big rig that's mounted, and you don't need to look at it. You can have a monitor here or your iPhone. It could transmit the visual, this visual, so you can just see it and record it or transmit it directly to YouTube. As it's rotating, you'd be able to see this interference changing. And I mean, so if you can do it horizontally, you're going to be proving the original Michelson-Morely experiment correct. And if you do it vertically, you can show that, I mean, you can measure the speed. So you need to tell me where I gave you the equations. I showed you how to develop the equations, what you should expect the speed to be, and what you should expect this speed to be. So I gave you the equations, so you should be able to calculate it. This should be at about, the way I saw it, it's about 11,000 meters per second. This depends on your latitude, because at the equator, it's obviously faster than at the North and South poles. North-South pole is basically zero. The equator is the fastest. I don't know how fast. So maybe we should calculate how fast it is at the equator and then do like a linear interpolation to the North and South pole. So we need, okay, so because I don't have an answer how fast the Earth rotates. So the Earth rotation, what is the velocity at the equator? Velocity at the equator is equal to what? So let's do this calculation. How do you do this calculation? So you know that the Earth does a complete circle around itself in 24 hours. So it's 1 hertz hertz is per second. So it's one cycle, one revolution. So it's 360 degrees. Okay. No undo. Okay, so the Earth gives us 360 degrees in 24 hours. Wait, I have an email. Let me check. La 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 la. Okay, it's just. Actually, it's 2 emails. Who is this? This is one bill. What is this? Oh, very nice. I ordered a headset, so that's good. That's the bill for that. That's good. And this is a normal payment. Everything should be fine. That's fine. How much? They don't say how much. Okay. They're not telling me how much they're going to charge me. That's good. Always a good thing not to tell me. Okay, so the next question that I want to ask is very important. La 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 la. La 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 la. Okay, so what's the next question? Please tell me the next question. Please. What's going on with this? Microphone is good. Everything is very nice. So it's 360. Okay, 360 degrees per 24 hours. And we want the velocity in meters per second. Okay, so we need to switch hours to seconds and degrees to meters. So what is the radius of the Earth? If we would know the radius of the Earth, we would know how many meters is 360. So let's go check it. So what is the radius? What is the radius of the Earth? The radius of the Earth is 63. That's good. It's 6378 kilometers. Okay. So it's 6378 kilometers per 24 hours. So 24 hours, so here's a trick. You can multiply 24 hours. How many minutes? It's 60 minutes. So you multiply 1 hour is 60 minutes. So there are 60 minutes per hour. So 60 minutes per hour is equal to 1. You're allowed to multiply by 1. When you multiply by 1, you can drop the hours. Now you want to drop the minutes. So it's 60 seconds per minute. So it's 60 seconds per 1 minute. That's still 1. You're still multiplying by 1 and you're dropping the minutes. So it's 60 by 60 and you have the seconds at the bottom. So 6 times 6 is 36 with 2 zeros. And that's seconds. So this is a revolution. So we're traveling at this many meters per second. So 6378 divided by 3600. 100. Where's the calculator? Jesus. Calculadora. How do you pin to taskbar? Okay, so we said 6378 000 so it's about 6 million. What? 6 million meters. Did you know that? The radius is 6 million meters. Oh wait, that's the radius. No, we need the circumference. The circumference is that times 2 pi. It's 2 pi r. So times 2 pi. So 2 pi r gives you the circumference. All right. So 6 million times 2 is equal to, that's already almost 13 million, times pi Where is pi? There is pi. Is that pi? Yes. So it's equal to, that's a very big number. It's 40 million. Okay, so it's 40 million meters. So it's 40 times 10 to the 6 meters divided by 3,600. Well, it's divided by 36 times 10, 3,600. So this becomes 4. Okay, so it's 40 divided by 36. So just divide this by 36. And that's about 1 million. So it's 1 million times 10 to the 4th meters per second. So it's about 1 million times 10. 1 million is 6, so it's 10 to the 10th. So it's 10 to the 10th meters per second. That's the velocity? 10 to the 10th meters per second? What? 10 to the 10th? Well, 10 to the 6th is a million meters per second. So that's way too fast. Because what? So 6, that means it's faster than the speed of light. 10 to the 8th is the speed of light. So we're rotating faster than the speed of light. That's good. Always a good day when you discover that you're moving faster than the speed of light. All right. Well, where did we go wrong? 360 is 2 pi r. All right, so it's 2 pi r. R is about 7. This is wrong. It can't be 6,000 kilometers, maybe 6,000 meters. No, it is. It says based on, what is the radius of the Earth? 6,000 kilometers? That's huge. Okay, let's assume it's 6,000 kilometers. We didn't get that wrong. Okay. 6,000 kilometers. So 2 pi r is the circumference. So it's basically 6 times that. So 6 times 6 is 12,000 kilometers. And that's divided by, so it's just 12,000 kilometers divided by 3,600. That's all. How did I get this so wrong? 40 times 10 to, where did I get this number from? This is why it's always better to do things without a calculator. First do it like more or less. So this is basically 6 and this is 6. So it's 6 times 6. 6 times 6 is 36. And this is 1,000 times 1,000, so it's 1,000,000. Yeah, so it's 36 million. You can say it right away. It's 6 times 6 is 36, and this is the million. So it's 36 million, and this is 3,600. So 36 by 36, okay, so it's a million, so it's 1 million divided by 100. So it's 6 minus 2 is 4. All right, so it's 4. So it's 10,000 meters per second. That's still significant. This is completely wrong. I don't know how I got this. I don't know what I did here. But this is 6 times 6 is 36 million, but 36 by 36 is 1. So it's a million, which is 10 to the 6 minus 2 zeros. So it's 4. This is meter. No, you don't need to say that. It's already, you have the meters here. So it's just 10 to the 4th. That's the answer. So we're traveling right now at 10,000 meters per second. Okay. So it's not 500. So this is good. If the speed is about, well, at the equator. So let's say in Ohio, it's half that much. That's amazing. So should they have discovered it? I was assuming 500 meters per second, but now I see it's 5,000. Wait, what do you mean 10 to the 10th? What did I undo? How much did I undo? I just wanted to undo that. Okay. So this is 10,000. This is 10 kilometers per second. We're moving at 10 kilometers per second, or 10,000 meters per second. This is 500. So this is a tenth of what we're actually moving at. We're moving at 5,000 meters per second in Ohio, basically. So at 5,000 meters per second, what should be the effect? What should be the effect? Should they have noticed it? So how did I get this number so wrong? Let's see. La 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 la. Wait, somebody's talking? Guts. No, let's talk now. If you're depressed, then talk to me right now. If you're not, if you don't mind everyone hearing it. Who are you? Guts. Join me now. Well, are you going to answer? Let's DM him. Oh, we've spoken before? What is this? Is this Andrew? I think it's Andrew. Yeah, it's Andrew. What's going on? What's going on with him? Oh my God. All right. Hopefully he'll be okay. Okay. So we got wrong numbers. Our numbers were incorrect. The question is, by how much did we screw it up? So let's go back to the equation of the interferometer. Like, what do we expect? What is the interferometer equation? Wave mechanics. Oh, scientific calculation of what? I think this is. I don't think this was it. Stop saying. There's no name. Quantum gravity. Second page. The speed of space. The speed of light. Where's. There it is. Michaelson-morely. This is probably the first time. Fiber optics. No. Michaelson-morely. There doesn't seem to be an equation here. Okay. Polarization, dark matter. We have oh, this is Galileo. 3D Maxwell, Stern, black hole, 3D inertia, more reflectors, no moving parts. What is it? There's nothing here. Notice. Proof C. Derive Planck. Andrew. This looks interesting. So we actually, we took somebody's derivation of the interferometer. I want to find it. I'd like to find how we used it. It's going to be very difficult. GR from Newton. Nothing. Wave mechanics. Probably not. Scientific calculation of what? I don't know what this is. Second Newton's the speed of. That doesn't look like it. Racism. Lorentz predict ether. Maybe this. The difference in time. The difference in length. The difference in time. That doesn't help me. So this is the difference in time times the speed of light is the difference in length. So lambda is 0.65. What is n? delta L, the difference in length over some lambda that we're using, is equal to the number, okay. N is the number of wavelength we expect. Anyway, so delta L is this thing, the difference in length that we expect. I need the next page, predict ether experiment. But every time we pick it up, it goes to the back. Predict the ether experiment. Where did this one come from? Quantum, the speed of space. Could be the speed of space. The speed of light. Outline. This one. This is a calculation continued, but we need the previous page. This is how many ends do we expect? How many wavelengths do we expect? Rope wave polarization, maybe dark matter, Galileo, intro to physics, double slit, Maxwell, black hole, inertia, reflectors, doubt it. No moving parts, I don't know. Newton, graviton, sinus, maybe it's sinus? Proof of what? Constant speed of light. Derive Planck. Andrew, Maxwell, Newton, start over. Bathtub. This one. Calculate the number of ticks. Okay, this looks like it. So, okay, what do we got here? So the number of wavelengths, I don't know, what is T? Number of times, number of ticks. It's 2dV squared over c squared lambda. That's the number of ticks over 90 degrees. I gotta go to sleep, so I have to wake up early. Okay. Oh, yeah. my broken headset is digging into my skin. It's like a broken bone. Okay, what do we got here? It's basically, so V is, I think V is the speed we're moving at. So this is the assumption that V is vertical. So it's basically the same. All the calculations I did are with respect to the ether, and just so happens it's basically the same as the ether moving sideways at the equator. So it should give us a similar number. So 2D this is, I don't know what this is. It's already divided by C. So it's 2D over lambda times V over C squared. So 2D over lambda so it's the same. So assuming the speed, you could say it's half of that speed, but it's about 300 meters. That's the next page. 2D is just 2 meters, so it's just 2. It's 2D over lambda 9. I don't know. We need to watch the video. I don't know. Anyway, the end of this conclusion was that it's about 300 meter arm should do the trick. So it's about 100 meter arm should do the trick. And they only had 1 meter. So, and this is assuming one, this is just to get 1 tick. 1 tick. They needed about 100 meters, and they only had 4 meters. Maybe they saw a signal. I don't know. It's I don't have their data, so there you go. The point is that good. I'm tired, so I have to go to sleep. Okay. So getting back to today's design, where is it, Michaelson? Let me show it again. Fiber optic. Is it this one? What's this? Yeah. So it's 10,000 meters per second. That's all I wanted to say. To show. So it's from the calculations that I remember, it's about 300 meters or 100 meters. So I don't know if this will do the job. It might do the job. If it doesn't do the job, laid out and then display, you should see something. And if you can do it both vertically, the number should be a little bit off. So vertical should be 10,000, around 11,000 meters per second, and horizontal, if you're at the equator, apparently it's 10,000 meters per second. But if you're like somewhere around Ohio, I would say you have to interpolate from. It's probably if it's about 10,000 meters per second at the equator. It's not 10,000, by the way. It's probably 11,000 because it's not 6 times 6. 2 times 3.14 times 6.4. It's probably more like 11,000. Let me do the calculations properly. So 6378 6378 times 2 times pi is equal to 40,000. Or 40 million, yeah. It's about 40 million. It's exactly 40 million divided by 3,600. It's 11. Yeah, so 11 kilometers per second, just like the ether. It's amazing this is the same number. So the ether comes down at 11,000 meters per second, and at the equator, the Earth is moving at 11,000 meters per second to the east. These are just coincidental. Anyway, if you want to interpolate your velocity, the surface of the Earth velocity from 11,000 at the equator, it's 11,000. It's about 11,000 at the equator. So what would it be at any latitude? So the way you calculate that. So this is the Earth. This is the thing, the equator. So basically the question, so at any latitude, so the latitude, I don't know what the latitudes are. I think they're angles. I think they're calculated as angles. The latitudes are just angles. So one latitude, so they're all the same. The latitudes. So if you're halfway, if you're over here, then the speed of the effective speed of the ether that you should experience, well, it's zero over here, it's 11,000 over here, so halfway through is at half. How does the speed drop off? Is it linear? Is it a linear drop off? It might be a linear drop off as the angle theta. So this is the angle theta. Whatever that is, that's the angle. Usually that's the angle phi or phi. Usually it's the angle phi. Okay, the angle phi. How does the speed vary with the angle phi relative to the angle theta? So, but there's no theta. There is only phi. No, there's no theta. So how does the angular velocity change in a sphere? My intuition is that it's linear. Somehow my intuition is that it's a linear difference for every angle theta, for delta theta. So the question is, dv as a function of theta, how does it vary? Or d phi? Oh, that's d phi. The velocity, right? Let's assume there's a velocity at every point. There is a velocity relative to the ether. Velocity, it varies as a function of phi. So how does it vary as a function of phi? So what is the velocity as a function of phi? what is it? Well, so it's just a different radius. So if we have a top view of the Earth, this is the top view. So this is the velocity at the equator, and this is the velocity halfway through the equator. The velocity at the North Pole is 0. So the question is every angle, every 1 degree, do all the degrees look the same from a top view? So I would say no. The first degree, you cannot tell the difference from the top view. And the last degree looks like it's very big from a top view. So in the beginning, there's no difference. So that's the answer. It's not linear. So it sounds like it's at 90 degrees, it's very big, and it's the sine. So in the beginning, there's no change. So let's take the velocity and multiply it by the sine. If it's sine phi, but in the beginning phi is 0, sine phi is 0. So in the beginning, so maybe it's cosine. So cosine is the full value. At the end, it's 0. So it's probably cosine phi. So it's the velocity at the equator times cosine phi, I'm assuming. It's basically the cosine. It's the projection. It's basically the projection to the bottom. So that's the cosine of the angle. Right? The cosine is this over this, but it's always the same. It's always the radius. It's 1. So it's this over this. So in the beginning, it's the original number. It doesn't change. For the first 1 degree, there's no change. The last 1 degree, there's a maximum change to 0. It goes to 0 very fast. So that's cosine. So is it? So this is the original value. It's the same. Cosine doesn't change. Cosine of this angle, the cosine between this and this, the difference is 0. The cosine of this and the cosine of this are both 1, approximately. So it's, or they say the cosine of theta is equal to theta. Anyway, I think it's the cosine. I don't know. It feels like the cosine. Something like the cosine. It's the projection. It looks like it's the projection towards the bottom. It's this guy. This is the sine. It's this guy, yeah. It's this over this. So it's the bottom projection. So when phi equals 0, cosine of 0 is 1. That's it. And when phi is equal to 90 degrees, the cosine of 90 degrees is 0. So the velocity, okay, it makes sense. So it's the cosine phi. So I don't know, you need to find out by the latitude. So I think latitude is divided by, like, the Earth is 360 degrees. So you need to find out your latitude. Your latitude is an angle. So wherever you're conducting this experiment, you need to look at you need to look at the map and find out your latitude. And your latitude is a degree. So you need to calculate. I don't know if they give you the number. Well, if I don't know if this is 0 degrees or where is 0. I don't know. Let's look at a map. Map. Is there latitude? There's no latitude lines. Let's ask for a latitude. Latitude. No, there's just places called latitudes. So we need to actually find a map with latitudes. Map with latitude. Images, latitude, longitude, finder on map, get coordinates. Okay. Okay, so what we need to do is, what, move this? No. Okay, so let's say we're in Ohio, name a place, Ohio. Ohio. How do you spell Ohio? Like this? So latitude is 40,000. That doesn't help me. What do you mean 40,000? Isn't it in degrees? It's 40, not 40,000. It's 40. So it's 40 degrees. So let's read about the coordinate system of the Earth. So Earth coordinate system. All right, the Earth's coordinate system refers to a set of spatial reference systems used to measure and communicate positions. GCS. What is GCS? I don't know. They said ECS before. Earth coordinate system. Oh, geographic coordinate system. My God. How is this so difficult? There's so many coordinate systems. Okay. What is the meaning? Latitude. More water. What is the meaning of more water? The angular distance north or south of the Earth's equator, measured in degrees along a meridian, has on it. Perfect. So that's all you want. So you want your latitude. Your latitude, so if you're 40 degrees in Ohio, then you take cosine of 40. So you take the cosine of 40 and you multiply it by 11,000. So 40 trig cosine is 0.76 times 11,000 is 8. It's 8,000, 8,500. Okay, so at 8,500, you plug that in into our equation. You plug it into our equation. I don't have the equation here. You find the equation, it's in the previous thing. 85. This one, I think, had it. It's pretty much this. So D is the arm. Lambda, let's do the calculation. So let's take this with us. That's NT. So let's take this with us. Copy. Do we have any more white space here? No. So what's the name of this one? This is calculate Ohio and number of ticks of horizontal. This is horizontal ticks. One second, I haven't checked on what's her name in a couple of days already. Favoritas. Oh, she's not favoritas? That's weird. That's really weird. Okay, what's her name? Let's check. Okay. Alright, whatever. Okay, so what do we want? What we want is Ohio, number of ticks at Ohio. So what do we got? So number of, so we need to paste. Okay. We can drop this. And this. Okay, so we'll take this. This is the number of ticks. So 2D, so let's assume some number. So this is equal to 2, let's say D is 100 meters. Lambda is 0.65, so it's 650 nanometers. V over C, it's about 8,500 over 300 million. 3 times 10 to the 8th squared. That should give you the number. So we can leave the one. Then we can multiply. If we get less than 1, then we just add more. Multiply this by a bunch. So let's get this out of the way. So this is 8,500 divided by 3 times 10. Okay, so 8,500 divided by 3 times 3 times 8, 10 to the 8th. That doesn't make any sense. Let's clear everything. How do you clear? Oh, garbage, okay. So let's do this first. So let's start with 10 to the 8th times 3 divided by 8,500 squared inverse. Okay. So it's 8 times 10 to the negative 10. That's step 1. So it's 8 times 10 to the negative 8. So this is 8 times 10 to the negative what? Negative 10. It's a very small number. Okay. So this is 200 over 650. It's 0.3. Okay. So 0.3 divided by 8. I wish I had done this before. So this thing divided by 8 is equal to divided by 10 negative. No, wrong. Start over, garbage. So again, let's start with negative 10. Oh, 10 negative to the, okay, times 8 divided by 0.3 inverse 375 million divided by, like, what are we're looking for the number of times. So this is what? This is meters per second and meters per second. This is meters per second, and this is meters per second. So what are the units? This is meters per second, this is meters, so this is unitless. Oh, this is meters, okay. So this is meters over meters, this is unitless. So it's just nano. So what is a nano? So a nano is the next step after. So you have micro. After micro, you have nano. So a micron is a million, and nano is 10 to the negative 9. So we need to multiply by 10 to the positive 9. Multiply by 9. No, we need to divide. Divide by 18. It's 0.375. It's not even 1. Okay. So 100 meters flat wouldn't give you even a single wavelength. You wouldn't see it. 100 meters flat, and this is 100 meters spooled. So of course, so if it's spooled, you don't expect anything. So you need to add more rolls. And even if you spool it out, it's not going to be enough. 90 degrees will give you a third. You might be able to see it. Over 90 degrees, you might be able to see a third of a wavelength. So let's just write it down. It's 0.375. It's 0.3, whatever. It's too small. You might not be able, I don't think you'll be able to notice it. You might not, this might be inconclusive. And this is if you spool it out. So let's double that. If you double that, it's just going to be 0.6. That's still not enough. Double it again, that's enough. So if you double this, it's 100 meters, 200 meters, 400 meters. Each 100 meters costs $300. So you need 4 on this side and 4 on that. You need 8. So it's $8,000. 8 times 100. $800? It was $300 for 100 meters, sorry. So 8 times 3 is $2,400. So it's beginning to become a formidably expensive operation. So you're gonna need some funding unless you're look, you can buy it on Amazon and return it. I don't know how they're gonna feel about you buying and whatever. I mean, I'd rather that's unethical. That's not nice to the people that produce it. You might ask them, listen, this is for like a very famous experiment. I just need to conduct the experiment and return it. So can I just borrow it? I'll pay you just for borrowing it. I don't know. And it's a lot of work. So if you're going to need and this is just for 1.2 wavelengths, but that's already significant. That's already completely visible. But you're beginning to appreciate what Michelson-Morely were up against, and they didn't even know. They did want like 4 meters, 8 meters. You see that it's useless. You see the numbers. And this is assuming 8,500 meters per second. That's a very big number. And that's barely noticeable because you're dividing it by the speed of light. And it's less than 1, and then you're squaring it, so it's even tinier. Below 1, if you square it, it becomes even smaller. It's a fraction of a fraction. It's a fraction squared. It's 8 times 10 to the negative 10th. It's really tiny. But the nanometer is +9. So everything cancels out. And you basically, you're right about 1. So that's the answer. Anyway, how long have we been streaming? Okay, it's 2 hours, but we figured it out. Look, when I first started this, I had no idea what's going on. Now, I'm giving you a solution right now. You need 800 meters, basically 800 meters at $300 per 100 meters. So it's $2,400. You need to set aside $2,400 and a lot of work because you're gonna have to spool it out. You can't use it all rolled up. If you want to use it all rolled up, you're going to have to invest in many, many rolls. So it's up to you what you want to do. And I don't even know if there's going to be a difference. You got to go through the calculations to see if there is a difference, if they're all rolled up. I don't know. Anyway, this is we live in exciting times as Tank or Dozer. Which one was it that said it? I can't wait for somebody to perform this experiment. I understand it's not cheap, but maybe a bunch of high schools can, like a county. Okay, we have a message. Maybe a county can work on this together. So it's 4 a.m. What do you want to do? You want to talk to me? You said you wanna call me. It's up to you. You just spoke to me. And I'm not in the mood for any debate. I'm not. Who's debating? You said you're depressed. Can you hear me? Are you watching the stream? Let me see. I can tell if you're watching. No, you're not. No one is watching. So what do you want to do? You said you're depressed. You said that you are depressed. You wanna talk. I have to wake up in a few hours. I don't really have to, but I need to. I gotta go. So it's up to you. I have to go to sleep soon. All right, everyone. We did it. This is it's a great solution. Cannot complain. Yes, I'm streaming. Yes, but I'm finishing up. I can call you private if you want. Are you still, sorry, depressed? After you finish, we can text for a minute. Okay. Give me a minute. All right, everyone. I think we're done. It's good stuff. We got a lot accomplished. I mean, this is experimental stuff. I wanted to make sure you have everything ready for this experiment. You should be able to conduct the experiment relatively straightforward. You have all the information in this video and the previous videos. Plus, you can talk to me, ask me. So this would be really amazing. You can do both experiments to prove the ether rain as well as the ether flow, the horizontal and the vertical experiments. It's up to you if you want to build it. For basically, I would say $3,000, you should be able to build the whole thing, make history. This is history in the making. This is disproving. It's difficult to say it's disproving Einstein because Einstein held the stick at both ends. He said in 1920 that the ether is gravity. He said in 1905 there is no ether. So he said everything. So whatever we get, he's not wrong. So, but it does violate the theory, the paper about the theory of relativity in 1905 that everyone believes in, except for Einstein. Obviously, he retracted it in his mind, but nobody cares. This should be absolutely revolutionary. All right, everyone. Thank you very much. Let's just check that the audio is still good. Believes it, except for Einstein. Obviously, all right, good video, good stuff. I'm gonna go back to looking at Zabine, what Zabine said yesterday. Really interesting. She's basically denying entanglement. She said there is no spooky action at a distance. It never happened. I don't know what to say. I mean, so I don't know. I don't know what's going on. I honestly don't know what's going on. I don't have a position on it at this point. I just want to finish my paper and get to writing the rest of my papers. So that's the next step. But I just thought up this experiment. So there you go. All right, everyone. I'm gonna go now. See you tomorrow. Bye.